Now let's work on a tiny floating point example. So in this one, like it just takes 8 bits floating point representation, which doesn't work out, but this is something that comes in handy. We have 4 bits for exponent and 3 bits for the fraction. Now, since I have 4 bits as the exponent, with the numbers that I can represent, it goes from 0 to what? To the power 4 minus 1, which is 15. And the bias is 2 to the power 4 minus 1 minus 1, which is 7. So I have a 7. If it's above 7, then it's positive. If it's below 7, it's negative. And I have 3 bits for the fraction. So this is the same thing, and we'll see how the numbers, different bit patterns represent this. So for this particular, I'm just focusing on the positive part. So the S bit is always 0, but it will apply if S is 1, you just get the negative numbers. There's nothing fancy about it. Now let's see basically how these numbers represent. So we go from 0, 0, 0, 0, 0 here, so all the way, okay, we increment it by 1 to 1, 1, 0, 1, 1, 0, and so on. So we start from 0, 0, 0, 0. Okay, in this case, remember my bias was 7, and in the case of now this is a denormalized number. In a denormalized number, let me write this here. In this case, E was 1 minus bias, and M was 0 dot fraction. Okay, so with this one, it's a denormalized number because the exponent is zeros. Since the exponent is 0, then it's a denormalized number. That's how I know it. And with this, then the E value is 1 minus bias, and where bias is 7, so the E value is minus 6. It's essentially the 1 minus bias. And what about the fraction part? Like, it's 0 dot frac. So this is essentially, let me see, minus 1 to the power 0, this is the sign bit, times fraction 0 dot 0, 0, 0 times 2 to the power minus 6. And the value that you get is 0. Fine. Now let's move on and let's look at the next one here. In this case, my fraction is slightly different. And let me work this out. So it's again minus 1 to the power 0 times 0 dot 0, 0, 1, that's the fraction, times 2 to the power of, again, minus 6. Now, what's this value? This is 2 to the power minus 3. So that's equals 2 to the power minus 9. 1 over 8 is 2 to the power minus 3. I'm sorry. And then 1 over 64 is 2 to the power minus 6. And that's it. And what about the next one? So remember, I'm just treating it like incrementing one by one. In this case, I will have you again do the same thing with this one. It will be minus 1 to the power 0 times 0 dot 0, 1, 0 times to the power minus 6. And now I can do that. This is 2 over 8, and this is 2 over 512. Now let's go ahead and look at other numbers. So you can see that by incrementing this, I am in the denormalized mode here. And then I can get in here until my fraction becomes 1, 1, 1, 1 here. And this number that I have here, this is the largest denormalized number. I cannot have a denormalized number that's larger than this. And with this, remember, like in the denormalized case, I had E was equals to 1 minus bias. Bias was 7. And then M was 0 dot frac. Now, when we do this, it's essentially this is 1, 1, 1. This is 7 over 8 here. That's 1 over 64. And then the result is 7 over 512. And this is the largest denormalized number that I can have in this representation. Now, if you increment the bit one more, then what we will get is this. Now, in here, we have the normalized numbers. You can see them here. This is the normalized region because the exponent is not all zeros. So when we get into this normalized numbers here, so in this region, in the normalized number region, in this region, we have a different computation, right? It's again, in this case, exponent E was equal to exponent minus bias, which was 7, and then M was 1 dot frac. Now with this, let's compute this value, which is the smallest normalized number. In this case, I can say that, what's the value of the E? E is exponent is 1 minus bias 7, so that's minus 6. Value of M is 1 dot frac, which is 0, 0, 0. And the value is essentially minus 1 to the power 0, that's the sign bit, times 1 dot 0, 0, 0 times 2 to the power minus 6. And this is essentially about 1.0 times this, and that's what we have, 7 over 512. Now let's see, what was the largest denormalized number? Let's go back, and it was 7 over 512. Write this here. So this was 7 over 512. So you can see the smooth transition from the denormalized numbers into the normalized numbers. If I hadn't told that this was like not the case, you wouldn't even realize it, right? Now, what about this one? In this case, well, the value here is minus 1 to the power 0 times 1 dot 0, 0, 1, okay, times 2 to the power minus 6 again, okay, and this is essentially 9 over 8, and the value is 9 over 512. So we can go all the way, and you can note that I can represent 1.0 like this, where in this case, you can see that the number that I have here, this is actually what? 7, which is actually equals bias. In this case, exponent equals bias. Whenever I have this, and then when I have my fraction part as 0, then I will have the value is minus 1 to the power 0 times 1 dot 0, 0, 0 times 2 to the power 7 minus 7, which is 1.0. Let's go ahead, and when we go up, then we start to represent larger number. Again, we are in this normalized mode, and in the normalized mode, remember that E was equals to exponent minus bias, and then the M was 1 dot frac. So value is minus 1 to the power 0 times 1 dot 110 times 2 to the power 14 minus 7, and this value is, this is 2 to the power 7, this is, and then you can represent what you get is 224. Now we go one more with this representation, and this is the largest normalized number. And in this case, my exponent is not all ones, it's just one below this. My fraction is all ones. And in this case, now the value here is minus 1 to the power 0, 1.111, okay, times 2 to the power, again, 14 minus 7, and this is 240. Now, what do you see? You can see that, when my numbers get large, the spacing between the discrete representations get also large. I have a representation, I have a binary representation for 224. I don't have a binary representation for 225, 226, or 230. The next one that I can represent was 240. Whereas, if you remember, when I was close to 0, I was able to represent the distance in between numbers were much, much smaller. This is basically the whole thing in one batch.